Friends, now here we are talking the chapter number 4. This is your chapter number 4, magnetic effect of current. So magnetic effect of current, there are the two words, magnet and current. So when a magnet is brought in the contact of the current, the needle shows the deflection. It was first time explained by the Oersted, therefore it is also called the Oersted experiment. OERSTD, Oersted experiment. He brought a needle in the contact of the current. Suppose this we have a coil, and when a needle is brought to it, so it deflected, the magnetic needle deflected, therefore it is called the magnetic effect of current. And for this many laws are given to explain this effect. Ampere also has given swimming law, Ampere swimming law. This you have studied in the 10th class. Then rules for the finding the direction of the magnetic effect. Fleming has given the right hand rule. If you stretch your right hand like this, your fingers and thumbs are mutually perpendicular on each other. So by this law, then left hand rule also has given. In the left hand rule, the direction, field and current. So if you stretch your left hand, your forefinger, middle finger are such as perpendicular thumb, okay. In this case, your right hand rule, both the perpendicular on. So by this, so Ampere's law, and by Fleming's left hand rule, Fleming's right hand rule, and by Oersted law, we will study about the magnetic effect of the current. It was also explained by the Biot and Sawart, by the Biot and Sawart. Therefore it is also called the Biot-Sawart law. So the Biot-Sawart has taken a wire XY, and when the current flows in it, suppose this is, he has taken a small element of length del L, current, its direction is current I, and the magnetic field is B. He has supposed here the AB is a small element. He supposed AB is a small element. Then the Biot-Sawart, he explained the magnetic field is directly proportional to the current. Magnetic field is directly proportional to the current. This is equation number 1. And he state the magnetic field is also directly proportional to the length, that is a del L, and this magnetic field is also proportional to the sine theta. I can say this is equation number 4. And also this magnetic field is inversely proportional to the square of the distance, to the square of the distance. So he assumed that 4 component, if we join this component by combining equation 1, 2, 3 and 4, so you will get here the dV is directly proportional to I del L sine theta. If remove the proportionality, there is a constant k is there, I del L sine theta, and suppose the value of k, that is for this medium, mu naught upon 4 pi. So it is dB is equal to mu naught upon 4 pi I del L sine theta, I del L sine theta upon r square. This is called the Biot-Sawart law. It was also explained by the Laplace, therefore it is also called the Laplace equation. Laplace equation is also called, where k, that is k is a constant, you can say the k is constant. Once again recap it, the Biot-Sawart law, the Biot-Sawart, he has supposed that XY is a wire, current I is flowing in it. He assumed the small element del AB of length del L, and angle is theta, at the point P, the distance of this OP, you can say the distance of this OP is R, and the angle is theta, and magnetic field V. So he stated that the B dV proportional to current, proportional to the length, proportional to the sine theta, and inversely proportional to the square of the distance. As you combined it, you got this dV is equal to mu naught upon 4 pi I del L sine theta upon R square. It is also called the Laplace equation. If I can take in the special case R is equal to 1, I can take I is equal to 1, del L is equal to 1, so I can get the dV is equal to, here we got the K, and its a unit is Newton ampere per meter square, and the magnetic field also have its unit Tesla.